Everybody, can you hear me on Zoom?
Yes, I can hear you, Yanis.
Thank you.
You're not very loud.
I think we'll go ahead and get started. Welcome. Thank you for coming this morning.
Amy, we cannot hear you.
Can I hear me again?
No.
Can you hear me better now?
No.
እንደዛም ብሎ እየተሰማ ነው ዙም ላይ ያለ
What about now?
Better.
Better? Okay. All right. So welcome for this is Fitsum's defense.
It's Amy. We still cannot hear you. Maybe Fitsum is wearing a microphone himself. That's why we can hear it.
How do you
All right. What about now, better?
Oh man, wonderful.
Can you help me? I don't want to. All right. Good morning again, third time. I'll introduce Fitsum. This is his PhD defense. Fitsum has a bachelor and master's degrees in agricultural engineering from Haromaya University, Ethiopia, and I'll read this, Bandras Hindu University from India. He has more than 5 years of research and teaching experience before he joined my lab in the fall of 2019, first as a research scholar, and then immediately after that, about a year or so after that, he switched to PhD in the spring of 2021. And he has been doing research in the area of optimizing agricultural water management, developing decision support tools, using crop simulation models, hydrology models, leveraging data from different sources, from ground sensors, above canopy sensors, UAVs, so on and so forth. He's done intensive research, and I'm happy to say that all the data he used for his PhD, he collected it. And what's also impressive is that while he was busy collecting data, running his project, he was able to publish more than 15 peer-reviewed articles. 3 of his chapters are already published. 1 is under review, and the last one is ready for submission. In addition, he has co-authored 2 extension fact sheets and 2 conference proceedings. He has given several conference presentations and workshop presentations and has received awards for his presentation, including from the American Society of Agricultural and Biological Engineers, from Florida section, and from the international meeting in Nebraska last year. So with that, floor to Fitsum.
Okay, thank you everyone for being here. So my name is Fitsum Teshome. I'm a PhD candidate at the University of Florida in the Department of Agricultural and Biological Engineering. Today I'm here to defend my PhD project. And the title of my PhD project is Optimizing Agricultural Water Management by Leveraging Data from Ground, UAV-based sensors, crop simulation, and artificial intelligence models. Without further ado, I'll jump to my presentation. So this presentation has 4 sections. In the first section, I'll talk about the general background, hypothesis, and problems related to our research project. In the second section, I'll talk about the main and the specific objectives. And in the third section, I'll talk about each chapter of my research project. And then in the last section, I'll talk about I'll give some remarks on the key findings of our research project. So as a background or introduction, as you all know that irrigated agriculture consumes a large amount of freshwater resources globally as well as in the United States. And this sector is also known for consuming a huge amount of groundwater withdrawal. For instance, globally, irrigated agriculture consumes around 40% of groundwater withdrawal. In the United States, this sector is also known for consuming around 60% of groundwater withdrawal. And this excessive usage of groundwater and in general water resources by irrigated agriculture has its own consequences. For instance, it might lead to water scarcity for municipal and the industry, even for the agricultural itself. In addition to that, excessive withdrawal of groundwater, it might lead to aquifer contamination. In addition to that, it might also cause high energy use. However, at the same time, we need more water to produce more food for the world's growing population. For instance, in the next 25 to 30 years, we need around 90% of freshwater resources to feed world's growing population. But the quantity and the quality of freshwater resources declining from time to time. So we have to find out to reduce the amount of water we use in agriculture and to improve the agricultural productivity. In South Florida, we have another layer of problems. Our hydrology is very unique. Actually, Biscayne Aquifer is the main hydrology in South Florida. This aquifer is the main source of water for agriculture as well as for municipal. So this aquifer is very close to the surface. Due to that, it's very susceptible for aquifer contamination, especially if we have excessive groundwater withdrawal. In addition to that, in South Florida, we have also very unique and problematic soil. This soil is very shallow with high gravel content. Actually, the gravel content of this soil is more than 50%. And this soil is also known for having low nutrient and water holding capacity. And due to that, frequent irrigation and the water application it's required to have an optimum agricultural production. So in order to solve these two problems, we have to find out a way to reduce the amount of water we use and to combat those unique problems in South Florida. And one of the solutions we can follow is by practicing efficient irrigation water management or by practicing efficient irrigation scheduling. By practicing efficient irrigation scheduling, one, we can reduce excessive water usage or we can reduce the amount of water we use in agriculture. Two, we can improve agricultural sustainability. And we can also reduce the carbon footprint that agriculture is causing on the environment. In addition, we can also lessen the burden of growers to spend more money on crop production. But in order to have efficient water management, we have to have a reliable data. Without reliable data, we cannot apply or we cannot practice efficient water management. Reliable data is very efficient for agricultural water management because we cannot manage what we don't measure and analyze. In order to analyze, in order to manage any resource, including water resource, first we have to measure it and then analyze it. That's the only way we can manage our resources. In this regard, digital technologies are improving the way we collect, analyze, and visualize the data. For instance, drone-based sensors, crop simulation models, and AI models and the computational resources are improving the way we collect data, analyze, and visualize data. However, agriculture lags very behind in adopting these technologies. So this research project purpose is to explore digital technologies for agricultural water management. So the main objective of this study was to improve irrigation water management by leveraging ground above canopy and the UAV-based sensor data with AI and the crop simulation models. And in order to answer this main objective, we have formulated around 5 specific objectives, and I'll talk about each specific objectives in the coming slides. So this is our research project. In this research project, we have grown a sweet corn and green beans over 32 plots under 4 irrigation treatment with 4 replication. And our irrigation treatments were arranged in RCBD. We used 16 plots for green beans and a 16 plot for a sweet corn. And we conducted this research project during winter dry season. Why we are interested to use or to do this research project during winter dry season. In Homestead, winter is a dry season compared to the other season. That's why we are interested to do or to conduct this research project during winter season. We don't want the rainfall affects our irrigation treatments. Our irrigation treatments were 1 full irrigation and 3 deficit irrigation treatments. And we used maximum allowable depletion, which is 50% of total available water content, as irrigation water management strategy to decide how much amount of water we should apply and when to apply. And we used linear move sprinkler irrigation system for our irrigation treatments. This irrigation system was equipped with VRI technology, variable rate irrigation technology. This technology gives the irrigation system the capability to distribute different amount of water across and along the field. So let's talk about the weather of our research site or in general Homestead. Winter season is a dry season in a Homestead. It only receives 8% of the total annual rainfall. And this season also known for having the lowest minimum and the maximum temperature compared to the other season in the year. So let me talk about the data we collected in this research project. We collected many data. One of the data we collected for this research project is UAV imageries. So we used DJI matrix drone with Xenon XCT2 sensor and RedEdgeMX sensors to collect multispectral and thermal imageries. We also collected artificial reference surface temperature that imitates non-transpiring and transpiring plants using a drone image or drone sensor. We also used ground-based IRT sensors to collect canopy temperature from the ground. This is one of the IRT sensor on the green beans plot. And this is when we're installing the IRT sensor. And this is the data logger, which we use to collect the canopy temperature. And then this is the actual configuration of the IRT sensors in our green beans field. So we collected soil moisture data using Keros 12 soil moisture sensor, and we also used local weather station as well as found weather station, which is 300 meters away from our research site, to collect weather parameter of the our irrigation experiment. And we also installed lysimeter for each irrigation treatment to collect the depopulation of the irrigation treatment. And this is the lysimeter, and these are the pipes we used to extract the amount of water collected in the lysimeter. And these are some of the softwares we used for our analysis. In addition to that, we also used Hypergator AI and the Hypergator supercomputer for this study. So for the irrigation treatment, what we did, we closely monitored the soil moisture content of the 100% irrigation treatments. And then when the average soil moisture content of the 100% irrigation treatments reached to maximum allowable depletion, we started the irrigation at that time, not only for 100% irrigation treatment, but also for the other deficit irrigation treatment. So to decide how much amount of water we should apply for the 100% irrigation treatment, what we did, we subtracted the average soil moisture content of the 100% irrigation treatment from the field capacity, and we multiplied that by root depths. For the other deficit irrigation treatments, what we did, we multiplied this full irrigation amount by fraction needed to create the deficit irrigation treatment. For instance, if you want to apply irrigation for 25% irrigation treatment, what we did, we multiply this 100% irrigation treatment by 0.5, and the same for the other deficit irrigation treatments. So as I was already told you, our irrigation system was equipped with VRI technology. This technology gives the irrigation system the capability to distribute different amount of water across and along the field. How this VRI does that? It controls the sprinkler head and the linear speed. For instance, when we want to apply 50% of irrigation, what the VRI technology did, it's turn on and off the sprinkler head every 30 seconds. But if we want to apply 150% irrigation, what the VRI technology do, turn on the sprinkler head for the whole time and reduce the linear speed by 50%. So we also collected agronomic and phenological data for this study. We collected plant height, width, and biomass biweekly, and we also did final harvest at the end of experiment, and we did the final harvest from the two inner rows as you see on this figure. Why we did that? To avoid or to minimize border effects. And we also collected date of emergency, flowering, and a harvest. So with that, I'll jump to the first chapter of my research project. This chapter objective was to evaluate advanced phenotyping based on UAV imaging and machine learning for monitoring crop responses to different irrigation levels. You might ask how this is related to agricultural water management. So in order to practice any agricultural water management, we have to know how the crops are responding to different irrigation treatments. Once we know the crops are responding to certain type of irrigation water management, then we can practice those irrigation water management so that we could have an optimum crop production. In addition to that, advanced phenotyping can provide crop monitoring without plant or soil destruction. So the result of this study already published in the Journal of Computers and Electronics in Agriculture. You can use this QR code if you are interested on the paper. So what we did first, we collected multispectral imageries using red-edge MX sensor and the DJI matrix drone, and then we gathered the multispectral image, and then we used Pix4D mapper to generate DSM, DTM, and the orthomosaic image. Then we subtracted the DTM from DSM, which is digital surface model, and the digital train model. We subtracted the digital train model from digital surface model to get the crop surface model. That's UAV image estimated plant height. So once we have this plant height, we compared this estimated plant height with measured plant height. Once we know there is a good correlation between measured and estimated plant height, we use the estimated plant height to estimate biomass and yields. In addition to that, we also generated around 8 vegetation indices using the orthomosaic multispectral bands. And then we used these vegetation indices with UAV image estimated plant height to train and test 5 machine learning models. Actually, we used 3 nonlinear models and 2 linear models to predict sweet corn height and biomass. And then once we predicted the height and biomass, we compared those predicted or estimated height and biomass with measured height and biomass. So for the result, we observed that the crop surface model was able to accurately simulate the sweet corn height with good accuracy, especially for the combined estimated plant height had a good agreement with the measured plant height. Actually, the distart was almost 100%, and the mean absolute error was only 5 centimeters. So then we also observed that there was a significant linear relationship between UAV image estimated with biomass as well as yield. So once we know there is a significant linear relationship between these two parameters, we use that model to predict biomass. And as you see on this figure, there was a good correlation between estimated and the measured biomass for both fresh and the dry total biomass. So for the machine learning models, we were able to see that all the machine learning models were able to accurately simulate the heights, the sweet corn height and the biomass with good accuracy. However, we observed the nonlinear models performed better for biomass estimation, and on the contrary, the linear models performed better for the plant types. That's also maybe from the number of input features we use to predict plant height and biomass. For instance, for biomass, we use vegetation indices and plant height, but for the plant height, we only used the vegetation indices. So the number of input features we used to predict plant height and biomass might be affected the performance of the machine learning models, but overall, the performance of all the machine learning models were very good in estimating a sweet corn height and biomass. So as a summary, we can summarize that advanced phenotyping can improve agricultural water management by providing non-destructive and continuous monitoring of crop responses to different irrigation levels. And in this regard, UAV imaging and the machine learning algorithm can play an important role in providing improved plant phenotyping. With that, I'll jump to the second chapter of my research project. This chapter objective was to explore potential of crop simulation models in capturing crop responses to different irrigation treatments. So for this, why we are interested to do this? Because as I was saying before, in order to practice any irrigation water management, including deficit irrigation management, first we have to see how crops are responding. If they are responding negatively, we have to avoid that kind of irrigation water management. So in this regard, crop simulation models can be used to study crop tolerance to different irrigation water management, including deficit irrigation water management. So that's why we are interested to do this research project. And the result of this study also already published in the Journal of Agricultural Water Management. If you are interested on the result, you can use this QR code. So for this, what we did, we selected two DSAT models, a sweet corn and a green beans model, and then we used daily weather data, soil properties, and a crop management to set up these two models. And then we used the first season data to calibrate the model using yield coefficient estimator and a sensitivity tool. And then we used the second season data to evaluate the DSAT model, the two DSAT models, for simulating different plant phenological parameters. In addition to that, we also did ANOVA analysis to see if the irrigation is impacting or affecting the fresh yield and biomass. In addition to that, we also calculated the amount of water conserved and the water productivity of each irrigation treatment. So for the result, we observed that the full irrigation fresh yield was slightly higher than most of the treatment, especially during the second season. However, this difference in fresh yield was not significant at 95% confidence level. This means that by practicing deficit irrigation water management, we can produce comparable yield of fresh yield. We can produce comparable fresh yield. This means by practicing deficit irrigation water management, we can reduce the amount of water we use in agriculture, and then we can also produce a comparable fresh yield. For the DSAT sweet corn and the green beans model, we observed the DSAT sweet corn model was able to reasonably simulate dry biomass of a sweet corn with reasonable accuracy. For instance, the DSAT during the evaluation period was 0.97, and this model was also able to simulate the height and the yield with good accuracy. For instance, for the yield, the DSAT model performance was 0.97. And we also observed similar performance for the green beans model, where this model was able to reasonably simulate dry biomass with good accuracy. And this model also shown similar accuracy in predicting or simulating canopy widths and the heights. However, this model simulated the fresh yield good in calibration period than the evaluation period. Then we also calculated the amount of water we conserved using deficit irrigation water management. We observed that all the deficit irrigation treatments were able to save a significant amount of freshwater resources, especially the 25% irrigation treatment had a good amount of water conserved compared to the other deficit irrigation treatments and compared to the full irrigation treatment. In addition to that, we also observed the deficit irrigation treatments had a better water conductivity compared to especially the 100% irrigation treatment. However, the 25% irrigation treatment had a better water productivity compared to all the other deficit irrigation treatment and the full irrigation treatment during both seasons and for both crops. So as a summary, we can summarize that deficit irrigation could be water conserving strategy in irrigated agriculture without significantly affecting crop yield. And in this regard, this art model is a useful tool for decision making related to agricultural water management strategies. With that, I'll go to the chapter 3. Chapter 3 objective was to leverage crop simulation and the machine learning models for soil hydrology dynamics modeling. So as I told you before, in order to have efficient water management or in order to apply efficient water management, we have to have a reliable data such as evapotranspiration and the soil moisture content. Without having these two parameters or reliable data, we cannot practice or we cannot apply efficient water management. One of the methods we can collect this information is by doing field experiments. Field experiments are very expensive and time consuming, but simulation models and machine learning models could be used to simulate evapotranspiration and the soil moisture without intensively investing in sensors and the field experiment. And the result of this study is also already accepted for publication in the Journal of Computers and Electronics in Agriculture. So for this, what we did, we already calibrated and validated this art model. We used these two models to simulate soil moisture content and the evapotranspiration. And then we compared the simulated soil moisture content and evapotranspiration with measured soil moisture and the evapotranspiration. And we also trained 3 machine learning models using Hypergator AI. And then we predicted the evapotranspiration and we compared this result with a measured evapotranspiration. So before going to the result, let me tell you how DSAT simulates evapotranspiration and the soil moisture content. DSAT simulates evapotranspiration by following 2 steps. First, it's used Priestley-Taylor ASCII or FAO56 Penman-Montes method to calculate potential evapotranspiration. And then it divides this potential evapotranspiration into potential transpiration and the potential evapotranspiration, potential transpiration by considering leaf area index and the energy extinction coefficient. So once we have potential evaporation and the potential transpiration, by considering the soil limitation, the model reduces the potential evaporation into actual evaporation. And by considering the crop limitation, it reduces the potential transpiration into actual transpiration. So once we have actual transpiration and the actual evaporation, by summing 2, it will give us actual evapotranspiration. For the soil moisture content, this art model first use USDA curve number method to calculate runoff. Then after calculating runoff using USDA curve number method, it subtracts the runoff from rainfall and irrigation to get the infiltration. And this model also assumes that any infiltration which is above field capacity is considered as depercolation. So once we have previously simulated evapotranspiration, depercolation, by subtracting these 2 variables from the infiltration, it will give us soil moisture content. So once we have this simulated evapotranspiration and soil moisture content, what we did, we calculated the crop evapotranspiration using measured data. First, we used soil water balance approach to calculate our evapotranspiration, but during our experiment, during most instances, our lysimeter were not filled with water, but we calculated the evapotranspiration with available depercolation data, but the result or the data we got is not reliable as we were expecting. Due to that, we neglected or avoided this method, and we used another method. We call this method soil moisture approach method. What we did, we subtracted previous sub-hourly soil moisture content from current sub-hourly soil moisture content, and we created time series of sub-hourly soil moisture change, and we plotted that against time, and we segregated the wet period from the dry period. In the wet period, we considered that there is a depercolation data, but we don't have those depercolation data. and the evapotranspiration during this time is very negligible compared to the dry period. And we only use the dry period to calculate the evapotranspiration of our green beans and the sweet corn plots. So for the result, first, we used the 2D set model to simulate soil moisture content and evapotranspiration. The result has shown that the green beans model was able to simulate green beans soil moisture content with good accuracy during both calibration and evaluation period. Actually, the mean absolute error during both period was 0.03 centimeter cube per centimeter cube. And we also observed similar result for the sweet corn, where this model was able to simulate soil moisture content of the sweet corn plot with good accuracy, and the mean absolute error for the two periods for calibration and evaluation period was 0.05 centimeter cube per centimeter cube. And we also observed that these two models, these are models, were able to reasonably simulate evapotranspiration of green beans and the sweet corn. However, the accuracy of these two models was not good as that of for the soil moisture content. And then we used the machine learning models to simulate evapotranspiration. We observed all the machine learning models were able to simulate the sweet corn and the green beans evapotranspiration with good accuracy. However, the light gradient boosting model performed better than all the other machine learning models in simulating evapotranspiration of green beans and the sweet corn. So as a summary, we can summarize that close monitoring of soil hydrology dynamics is crucial for efficient water management. And in this regard, machine learning and DSAT models could be convenient tool to produce reliable soil hydrology information to optimize agricultural water use. With that, I'll jump to the fourth chapter of my study. This chapter objective was to develop machine learning and deep learning models to predict sub-hourly soil moisture content of grain beans and the sweet corn plots under different irrigation levels. So there are different ways to monitor soil moisture content. There is the traditional method, which is gravimetric method. Even though this method is considered as a reliable method, but this method is very tedious. It requires a lot of time and energy to have a time series data. In addition to that, soil moisture sensors also could be affected by environmental and soil factors. So local calibration is essential to have a reliable data. But nowadays, artificial intelligence models are being used to identify hidden relationship between different parameters. So that's why we wanted to leverage these AI models for simulating sub-hourly soil moisture content of green beans and sweet corn. So for this, what we did, we used HyperGator AI to simulate 5 machine learning models, and we predicted the soil moisture content, and we compared the simulated soil moisture content against major soil moisture content. In addition to that, we also developed a deep learning regression network from scratch, and this model had 3 layers: input layers, which receives the input features, and these are the input features, and this layer, this deep learning model was also had second layer, we call it hidden layer. These layers are the layer which learned complex relationship between input features and target variable. And the last layer of this model was the output layer, which give us the predicted soil moisture content. So once we have the predicted soil moisture content, we compare that against measured to see how the model is performing for simulating soil moisture content of green beans and the sweet corn. So first, we try to see how the input features are correlated with the target variable, and we observed the electrical conductivity for both crops had a better correlation with target variable, which is the soil moisture content, compared to the other input features. So for the machine learning models performance, we observed all the machine learning models performance was more than satisfactory in simulating sub-hourly soil moisture content of sweet corn, but the extreme gradient boosting model and the light gradient boosting model performed better than all the other machine learning models in simulating sub-hourly soil moisture content of sweet corn. And we also observed similar results for the green beans model, where all the models' performance was more than satisfactory in simulating sub-hourly soil moisture content of green beans. However, as that of the sweet corn plots, we observed this light gradient boosting model and the extreme gradient boosting model performed better than the other machine learning models in simulating soil moisture content of green beans. And then we compared the performance of traditional machine learning models with the deep learning model. And we observed the deep learning model performance was less than extreme gradient boosting, light gradient boosting in random forest. However, the performance of this model was better than KNN and the cut boosting model. But we didn't stop there. We also compared the performance of the traditional machine learning models with deep learning models by combining different metrics. But from that analysis also, we observed the light gradient boosting model and the extreme gradient boosting model were performed better than the traditional machine learning models and the deep learning models in simulating sub-hourly soil moisture content of green beans and the sweet corn, as you see on this figure. So as a summary, we can summarize that soil moisture information is vital in close monitoring of crop water status and for efficient irrigation scheduling. In this regard, artificial intelligence model such as machine learning and deep learning model can play important role in modeling soil moisture of agricultural fields from easily accessible soil and weather data. With that, I'll jump to the last chapter of my research project. This chapter objective was to explore ground and the UAV-based thermal and the multispectral data for quantifying crop, sweet corn, and grain beans evapotranspiration. So there are different ways to quantify or to calculate evapotranspiration. We have weather method, we have soil method, and plant method. However, in South Florida, we have very fluctuating weather condition, and our soil is very problematic. So any evapotranspiration method, which depends on these two factors or variables, might have some inconsistency. So that's why we are interested to use plant physiological parameters for quantifying evapotranspiration. For instance, when plants are exposed to water stress, they reflect physiologically by altering their canopy temperature or their spectral reflectance. So if there is a capability to see how plants are altering their canopy temperature and the spectral reflectance, that change to evapotranspiration. That's what we did in this research project. First, we used canopy temperature-based stress indices. We used crop water stress indices and the operational simplified surface energy balance model to quantify evapotranspiration or actual evapotranspiration for grain beans and the sweet corn. First, for the crop water stress index, what we did, we selected the canopy temperature using these criteria from non-stress plots, sunny days, a day after rain or irrigation event, and 2 hours before and after noon. And then using this canopy temperature, we regressed that against vapor pressure, and then we developed a linear regression model between VPD and this canopy temperature. Then we used the slope and the intercept of this linear regression graph to calculate the canopy temperature of a stress plant and the non-stress plant. Actually, for non-stress plant, we used VPD, which is vapor pressure deficit, and for non-stress plant, we used VPG, which is vapor pressure gradient. For the CBAP, actually for the crop water stress index, we used ground-based IRT sensors for canopy temperature. But for the CBAP model, we use a drone image. What we did, we calculated the mode of the canopy temperature of each plot to get the surface temperature. To get the hot or hot temperature, what we did, we calculated the mean of the upper 95% canopy temperature. And for the cold, we calculated the lower 50% of the canopy temperature from each plot. And then once we have these three variables, we calculated ET fraction, and then we multiplied this ET fraction by reference evapotranspiration to get actual evapotranspiration. In addition to that, we also used a spectral reflectance-based crop coefficient. What we did, we developed a linear regression model between vegetation indices and the crop coefficient using the first season data. And we used the second season data to predict crop coefficient. And we predicted the crop coefficient using the second season data. And we used that crop coefficient to estimate evapotranspiration. And we compared the performance of the estimated evapotranspiration with the measured evapotranspiration. In addition to that, we also trained 4 machine learning models for estimating evapotranspiration using difference evapotranspiration and the vegetation indices. So for the result, we observed that both crop water stress index and the CBAP model were able to quantify or estimate evapotranspiration of green beans and the sweet corn with a reasonable accuracy. However, the performance of the crop water stress index was better than the CBAP model in estimating the crop evapotranspiration of green beans and the sweet corn. And for the vegetation indices, we observed the NDVI estimated the evapotranspiration with good accuracy for both a sweet corn and a green beans model. And all the other vegetation indices we evaluated to simulate evapotranspiration also performed similarly like that of NDVI to simulate evapotranspiration of green beans and sweet corn plots. And we also observed all the machine learning models performance was reasonable in estimating evapotranspiration of green beans and sweet corns. Especially the cut boosting model performed better for the sweet corn model, and the Kenyan model performed better than the other machine learning models in simulating evapotranspiration of green beans. So with that, the summary for this chapter is capturing crop physiological parameters such as thermal emittance and spectral reflectance could be used for irrigation scheduling. And in this regard, ground and UAV-based sensor play an important role in providing reliable thermal and multispectral data for agricultural water management. With that, I will end this chapter. So in general, our project conclusion or research project conclusion is close monitoring of crop soil responses to different irrigation water management is essential for enhancing agricultural water use. And ground-based IRT sensors have a potential to closely monitor crop responses to water stress that could be used for agricultural water management. And the UAV-based thermal and the multispectral image could be an alternative for monitoring crop responses to different irrigation levels. And the AI and desert models can play important role in offering valuable support in decision-making regarding irrigation strategy. With that, I will finish my presentation. Finally, I would like to acknowledge my advisor and chair, Dr. Hyman Pavel, for his incredible support during my PhD study and during my stay here in Trek. And I would like to also acknowledge my committee members, Dr. Gary Tugumbom, Dr. Bruce Schaffer, Dr. Yanis, and Dr. Aditya Singh for their incredible support during my PhD study. And I would like also to acknowledge my current and the previous lab members for your helping hand during my PhD study. And I would like also to acknowledge Mr. Jose and his crew for their help during the experiment. And I would like also to acknowledge USD and IFA for providing funding for this research project. And I would like also to acknowledge UFIF's Agricultural and Biological Engineering Department and the UFIF's Tropical Research and Education Center for partially supporting my PhD study. With that, I will finish everything. Thank you. Yes.
Yeah, thank you very much, Jen. Thanks for where you going further. I appreciate the fact that you are acknowledging it. Certainly the studies that you've done. Things that I want, even though I know this was not. Have you given any thought to how some of these findings knowledge can be translated into some practical idea? And also, if you have done any sort of measurement, what that would be.
Okay. Yeah, thank you so much. Okay, thank you. Those are good questions. So the first question, if we can use this result for growers, or if we can recommend anything for the growers. So in our case, we are not recommending the growers to use these tools, but what we are saying is we can develop irrigation water management strategy using these tools, and we recommend growers to practice that irrigation water management. So these are tools to select best irrigation water management. So researchers or anyone who is interested on those kind of tools can use those tools and then develop a good irrigation water management, and then recommend growers to practice that irrigation water management. We cannot say growers can use those tools or they have to use those tools. We are saying researchers can use these tools to develop best irrigation water management. For the second one, the graph I showed that's the real amount of water saved during our experiment during the first season and the second season. So we saved a significant amount of irrigation water by practicing deficit irrigation water management. So a significant amount of water is saved by practicing deficit irrigation water management.
What he really is looking at really there has to be a lot of data